So in this module, we're going to run through an example talking about how we can use assumptions about equilibrium chemistry, the definition of PM, and formation constants and conditional formation constants to calculate the concentration of free metal ion at any point during an EDTA titration, and thus how we can model and predict the shape and exact value of the PM at any point on an EDTA titration curve, just knowing the original concentration of the metal ion, the value of the equilibrium, the value of the conditional formation constant, and the concentration of the EDTA titrant. In terms of predicting the shape of the EDTA titration curve, the basic idea is that we are going to divide the course of the titration up into three regions. In the first region, we are prior to the endpoint volume, and thus we have more free metal ion than we do EDTA added. As a result, we have a greater concentration of our free metal ion than complexed ion, and this allows us to make specific assumptions about how to calculate the PM value at points prior to the equivalence point. At the equivalence point, the primary assumption is that the concentration of the free metal is equal to the concentration of the EDTA, and thus we are in an equilibrium situation where any free metal ion present in solution has been released out of the metal EDTA complex. The third region of the titration curve then is everywhere after the equivalence point, where now we have excess EDTA and we have significantly greater EDTA concentration than we do free metal ion. And so by using these assumptions in the appropriate region, we can predict the concentration of the free metal ion and thus the PM, calculate the PM value with good certainty and minimal error. So we're going to walk through an example with a calcium titration to show you how that works. So here's our setup for our example. We are performing an EDTA titration where we have 50 milliliters of an aqueous solution of calcium. And in this case, even though in the course of a usual titration, we would not know the concentration of calcium at the start of the EDTA titration, for the sake of showing you how to model an EDTA titration curve, we're going to assign a value to the analyte of 0.0400 molar. So for there would be no way to model the EDTA titration curve without knowing the concentration of the analyte. So unlike a typical EDTA titration that you would perform in the laboratory, in this case we start out knowing the concentration of our analyte. It is a 0.04 molar calcium ion solution. Total volume is 50 milliliters. During the course of our experiment, we titrate it with 0.08 molar EDTA, and we will have buffered it with ammonia to a pH of 10. We would probably use an Areochrome T-black indicator with this, just as we did in our hard water titration, which should function reasonably well at a pH of 10. And so we would see an endpoint color change of kind of the pale red to that sometimes difficult to see blue in this titration. What we want to do in terms of modeling the EDTA titration curve is we want to calculate the calcium concentration and thus the P calcium value, the negative log of the calcium concentration, at three different points. These are going to be one in each region. So first we're going to do a calculation in region 1, which is prior to the endpoint. There's 5 mils of EDTA solution have been added. We're going to do a calculation at the endpoint once 25 mils of EDTA solution has been added. Then we're going to do one in region 3 past the endpoint where 26 milliliters of EDTA solution have been added. And we're going to go through the assumptions that you would make to calculate the P calcium value in each of these regions. So a couple of things that we're going to want to have at our fingertips before we dive into this calcium titration example. And you've been asked to calculate a number of these things in the pre-lab. The first is we want to know how many moles of calcium we have in the solution. That will turn out to be really relevant. We want to know the endpoint volume. The endpoint volume can be calculated, of course, by finding the number of moles of calcium in the solution and then determining the number of milliliters of EDTA solution that we would have to add to reach the endpoint. something you should have done successfully in your pre-lecture exercise. And lastly, we want to know the alpha Y4 minus value. We want to know the equilibrium. We want to know the value of the formation constant, and thus we want to know the value of the conditional formation constant between calcium and EDTA, which is something that we calculated last time. So all those calculations should have been part of your pre-lab. I'd recommend, as I did in the instructions of D2L, taking a screenshot of your pre-lab or having your calculations from the pre-lab in front of you so you can add them to the course of this problem and you won't have to recalculate those values. So without further ado, let's dive into this, starting with region 1. We want to know what the P calcium value is going to be after 5 mils of EDTA solution have been added to the analyte solution. All right, so before we get into the specific calculations, just a couple more reminders. We would say that the equivalence volume is at 25 mils of EDTA added, which will mean a 75 mil total solution volume because we'll have the 50 mils of the analyte plus the 25 mils of the EDTA solution added. When we're calculating the P calcium value, that's the negative log of the metal ion concentration at any point during the titration. And we calculated the conditional formation constant last time for calcium and EDTA at pH 10, where we have an alpha value of 0.3 for the EDTA. The conditional formation constant is 1.34 times 10 to the 10th. And recalling from your pre-lab, the number of moles of calcium ion present in the unknown solution you should have found to be 0.002 moles. That's going to turn out to be relevant at each stage of the proceedings, but particularly in region 1. Okay, so jumping into the first region, we want to calculate the concentration of calcium that remains in solution after 5 mils of EDTA solution have been added. So of course, the chemical reaction governing our titration is 1 mole of calcium reacts with 1 mole of EDTA to make 1 mole of calcium EDTA complex, which we will abbreviate CaY2- as we usually do. In this region, in region 1, prior to the equivalence point, the calcium concentration is significantly greater than the amount of EDTA that we've added. And so as a result, since back reaction at this stage of the EDTA calcium complex should not be the main source of calcium in solution, we make the simplifying assumption that any calcium released back out of this complex is negligible due to Le Chatelier's principle because the calcium concentration is still quite high. Therefore, a calcium concentration before the equivalence point will be due only to unreacted calcium. And to find that number, how many moles of unreacted calcium we have, this is a strategy that we can apply throughout region 1 until we reach that equivalence point. And when we reach the equivalence point, that flips over and that becomes region 2 on the titration curve. So in region 1, anywhere prior to the equivalence point, we will find the concentration of the metal by figuring out how many moles of the metal have been complexed with EDTA, subtracting that value from the original number of moles, and then just dividing by the new volume of solution to get the calcium concentration. So our thought process goes like this. Originally, in our analyte solution, we had 0.00200 moles of calcium. That's 0.0400 times 0.05 liters. And we have added so far 0.005 liters, 5 mils, of EDTA solution. So if we've added 5 mils of a 0.0800 molar EDTA solution, we have thus far added 0.000400 moles of EDTA, which means that, because the calcium and the EDTA react 1 to 1, that 0.0004 moles of our original 0.002 moles of calcium have been removed from solution. This gives us an excess of 0.0016 moles of calcium that have yet to be complexed with EDTA. And so in region 1, we can then just calculate the calcium concentration by figuring out the number of moles of calcium that remain uncomplexed, dividing by the new total volume of solution, which is 55 mils. So that's 5 mils plus the original 50 mils. So our calcium concentration is now 0.0016 moles divided by 0.055 liters, and our free calcium concentration is 0.0291 molar. To figure out the P calcium value, we then simply take the negative base 10 log of our calcium concentration. The negative base 10 log of 0.0291 is 1.54. And after 5 mils of EDTA solution added, our P calcium value should be 1.54. Let's skip back to the titration curve for a second and see if that matches up okay. So at 5 mils of EDTA added, we should be right here. And so it looks like 1.54 mils is in good agreement with the titration curve that should correspond to the experiment that we're doing. So that's region 1. Notice in region 1, we don't have to make many assumptions about equilibrium because at this point in the titration, we just still have an excess of one reactant, and we can make the assumption that that's where essentially all our calcium has come from without introducing much error. Where we start to get into equilibrium considerations is in region 2, which is the endpoint. So now, moving on from the 5 mil, let's calculate the calcium concentration right at the equivalence volume, which is 25 mils of EDTA solution added. So at this point, the key is that to reach the endpoint, we had to put in the same number of moles of EDTA as we had calcium, because calcium and EDTA react in a 1-to-1 stoichiometric ratio. To simplify the math, we assume that in the initial reaction, all the calcium gets complexed by the EDTA, but then in the equilibrium, the Chatelier's principle takes over, and even though the formation constant between calcium and EDTA is quite large, some of the calcium is released through a back reaction of the calcium EDTA complex, and this Ca(Y2- complex spits out some number of moles of calcium and some number of moles of EDTA. So, because this will be an equilibrium situation, our work becomes a little bit more complicated. At this stage, and only at this stage, once we reach the end point, we have to bring the conditional equilibrium constant back into play. And so our K'(F) for calcium and EDTA at a pH of 10 is 1.34 times 10 to the 10th, as we calculated last time. And our Ca(Y2- concentration is equal to the number of moles of calcium in the system divided by the new total volume, which is 75 mils or 0.075 liters. So when this back reaction begins, the concentration of the calcium Y2- complex should be 0.0267 molar. And this is where we'll begin our problem. So to figure out how many moles of calcium are released from the Ca(Y2- complex, and hence the concentration of free calcium, we have to turn to the conditional formation constant, which says that the concentration of Ca(Y2- at equilibrium divided by the concentration of Ca2 plus times the EDTA concentration is equal to 1.34 times 10 to the 10th. Thinking this through in a modified ice table, the equilibrium concentration of Ca(Y2- should be 0.0267 molar minus X, and because our K'(F) is large, we're justified at this pH in dropping the minus X term from the numerator, and then because both the calcium and the EDTA are produced by the back reaction of the calcium Y2-, at the endpoint, we have X squared in the denominator. At this stage, we just have to rearrange and solve for X, which will be our calcium concentration. So we multiply both sides by X squared, we divide both sides by 1.34 times 10 to the 10th, and then we take the square root of both sides. So X, our calcium concentration, is equal to the square root of 0.0267 divided by 1.34 times 10 to the 10th. Our equilibrium calcium concentration at the endpoint should be 1.41 times 10 to the -6th molar. And if we take the negative base 10 log of that concentration, we find that the P calcium at the equivalence point is 5.85. And of course, a P calcium value, like pH or any log value, is unitless. So you just report it as the number. So this is region 2 on the titration curve. Region 2 is quite narrow compared to region 1 or region 3. Region 2 is literally just describing the calcium situation at the endpoint, where the concentration of calcium 2+ equals EDTA. Unlike region 1, this is an equilibrium situation then, because all the calcium in solution we consider to have come into the solution by the very small but significant breakup of the calcium Y2 minus complex. So as we should expect, we find that calcium concentration ultimately through the relevant equilibrium constant, which is the conditional formation constant. We have to make a simplifying assumption in the numerator, unless you really want to go full quadratic. But because our kf value is quite large, our k prime f value is quite large, we can drop the minus x term from the numerator that we would ordinarily get from the ICE table and calculate our pCa value quite directly. So that's region 2. That's how it's calculated right at the endpoint. And the key in all of these calculations is really keeping the region straight. And you need to resist a little bit. Hopefully, if I'm explaining this well, these steps all flow very naturally and they make a lot of sense. But you really need to sit down with a blank sheet of paper, try the problem again, and make sure you can understand the reasoning behind each of the steps and the assumptions that we make prior to the endpoint versus the assumptions that we make at the endpoint and the assumptions that we make past the endpoint to have success with these problems. I'm going to give you all no new lecture material on Friday, just a different titration curve modeling example to walk through. I would recommend that you walk through this calcium calculation one more time with a clean sheet of paper. When we're done, that's going to be your post-lab exercise. So I'll hold you to it, I guess, because we're at a distance. But I'll metaphorically hold you to it and make sure you're sitting down with a clean sheet of paper and you can follow this thought process again without constantly looking at your books or the notes or just trying to memorize it by rote. Make sure you can understand the chemistry assumptions that go into calculating these calcium values at different regions of the titration. This leaves us with only one more region, which covers all EDTA solution additions past the endpoint volume. So as an example, we're going to consider how we calculate the P calcium value once we've added 26 mils of EDTA solution. But the assumptions made in this approach would apply to every EDTA addition, every volume of EDTA added that's past the equivalence point volume. So whether we're adding 26 mils of EDTA, 27 mils of EDTA, 30 mils, 50 mils of EDTA solution, anywhere on that curve past the equivalence point, we make these same types of assumptions. So in region 3, everywhere past the equivalence point, the key chemical feature of the EDTA titration curve is now the concentration of excess EDTA added is significantly greater than the concentration of calcium 2 plus added. What's the reason for that? Well, the calcium 2 now can only come back into solution out of its complex with EDTA. Formation constant between EDTA and calcium is quite large, therefore calcium release is minimal. However, we're continuously adding fresh EDTA if we've gone past the equivalence point, and as a result then, the concentration of free EDTA in the solution is significantly greater than the concentration of calcium. So in this particular example, where we've added 26 mils of EDTA solution, we've moved 1 milliliter beyond the equivalence point, so we have added 1 milliliter of excess EDTA solution. To calculate our calcium concentration, we'll once again have to use some equilibrium considerations because all our calcium is being released by the CaY2 minus complex. But our jumping off point is we need to know how many moles of excess EDTA we've added so that we can calculate the concentration of excess EDTA. So for the concentration of excess EDTA, we have added 1 milliliter extra of EDTA, 1 milliliter past the endpoint, and the concentration of our EDTA solution is 0.0800 molar. As a result, we've added 8 times 10 to the negative fifth moles of excess EDTA. If we want to know the concentration of the excess EDTA, we take that number of moles, we divide by the total solution volume, which is 26 mils, plus the 50 mils of unknown that we started with, total solution volume of 76 milliliters, or 0.076 liters, giving us an excess EDTA concentration of 1.05 times 10 to the minus third molar. This is going to be an important number. I'll show you how to use it in a second. We also want to know what the concentration of the CaY2 minus complex should be in this situation. we know that there should be 0.002 moles of CaY2 minus in solution at this point. Calcium is the limiting reactant now at this stage of the titration because we've gone past the endpoint, so we can't make any more of this complex than we had moles of calcium to begin with. So we take that 0.002 moles of calcium, which made 0.002 moles of CaY2 minus, divide by the new solution volume of 0.076 liters. The concentration of our calcium EDTA complex should be 0.0263 molar. What are we going to do with that? Well, once again, we need to use equilibrium considerations because all our free calcium concentration is back reacting and coming out of this calcium Y2 minus complex right here. So once again, we use our conditional formation constant. The difference between the calculations in region 3 and the calculation we just did at the endpoint region 2 is now we know the concentration of the CaY2 minus complex. It's 0.0263 minus X. Once again, we neglect the minus X in the numerator because the amount of this complex lost to dissociation into calcium EDTA is quite small. The calcium concentration at equilibrium is going to be X. The EDTA concentration is going to be 0.00105 minus X. Again, we can neglect the X in the denominator in the EDTA term as well, because that will also be quite small compared to 0.00105. As a result, we now have an equilibrium constant where we know 2 of the 3 values. We know the concentration of CaY2 minus at equilibrium. We know the concentration of EDTA at equilibrium. All we have to do is solve for X by setting our K'F equal to its numerical value at pH 10, still 1.34 times 10 to the 10th. We are going to multiply both sides by X. We're going to divide both sides by 1.34 times 10 to the 10th. And if I've done my work right here, you should find that the concentration of calcium is equal to 2.0 times 10 to the minus 9th molar. If we take the negative base 10 log of that, we find that the P calcium value 1 mil beyond the equivalence point is 8.7. So again, hopefully if I've done my work reasonably well, you're looking at this and you feel that there's a lot of math here, but each of the steps make sense in succession. I would like you all to test yourself a little bit. I've drafted up a clean Word document that has the problem set up again at the end, and I've linked it to the D2L exercise. Your post-lecture review or your post-lecture problem is to replicate the assumptions and the calculations associated with modeling this EDTA calcium titration curve at the same volumes in region 1, 2, and 3, and see if you can come up with the same answers, and try it without constantly glancing at your notes and constantly glancing at the book while you do it. See if you can replicate the assumptions and go through the process. If after trying it again you find that there's anything unclear, please, please, please post to the message board, shoot me an email, hit me up during office hours. Let's have a chat about it. Let's discuss the assumptions again and make sure you have your process down pat. Once again, all we'll do Friday is we're going to give you an opportunity to sit down with a fresh problem and replicate this process for magnesium ion rather than calcium and see how the numbers change. I will see you on Friday.